Thanks everybody for coming, and thank you for the invitation to speak here. This is the first time I spoke here in this very spot is, 16 years ago. So yeah, it's it still feels like coming home. So I really always like coming back here. Thank you so much. You think you're getting free pizza, but I'm gonna make you work hard for it. Sorry, so you'll have to go through some theory with me. But for me, it's important that the talk be accessible. So please let me know if there's something that you have a question about. I'm going to talk today about work that we published at NURICS last year with my PhD student, Farnam Mansouri, who's jointly supervised at Waterloo, and my colleagues Hans Simon and Adish Singla at the Max Planck in Germany. So the topic of this talk is how can we avoid collusion, and what forms of collusion can we avoid in machine teaching? So in machine teaching, we want to convey something to a learning algorithm using only very few examples, but so that is also somehow how maybe coding and colluding with the learner. So we have to kind of strike a balance, and that's what this talk is about. Okay. And now my slides don't advance. Yes, they do. Okay. Consider the following hypothetical situation. You want to synthesize a program, say a C++ program or whatever, out of a small set of input-output examples that you kind of hand select. And in formal verification and program synthesis, people do spend some thought on how can we now tailor the algorithm that synthesizes the program to our knowledge of the selection mechanism for these input-output examples, right? We know that machine learning works better if the data is chosen carefully, but what I'm saying is it'll work yet even better if the machine learning algorithm knows something about how the data was chosen. Similar situation may happen in multi-agent communication. So if you have some decentralized system of agents and you want to design an agent that can communicate effectively, but you somehow have to, this agent may have to convey some of its language and what that means to other agents. And again, perhaps you could tailor agents to what you anticipate the source of information is. Maybe you know something about how it works, right? And I want to study that kind of idea, that kind of mechanism in a very abstract learning theoretic setting. So the abstract learning theoretic setting requires a little bit of formal notation. What I will be assuming always is that we have some domain set X, which I'll call the instance space. It can be, for example, the R2 is here, but it could be anything, any set. A concept is now merely a subset of that instance space. So in this example here, I'm assuming concepts can be rectangles in the R2. So a concept class is a set of concepts. So the class of all axis-aligned rectangles in R2, for example, here. And then we assume that the learning algorithm sees labeled examples that tell it something about the concept. The labeled examples are pairs where X is an element of that instance space. So here point to the R2, and the label L is a binary label that says whether or not this point X belongs to the underlying concept that the learner has to identify. So here the red points are positive examples where the label is 1. They belong to that particular rectangle that I've drawn there. And the blue points are negative examples because they don't belong to it. Okay, here is one of the simplest kind of concept class that you could imagine learning. This is a threshold over n grid points on the line. So your domain X here is just the natural numbers from 1 to some number n. And the learner has to identify an unknown threshold that lies somewhere on one of those grid points. Everything to the one side is 1 and everything to the other side is 0. Okay. So you could assume that the labeled examples presented to the learner are chosen at random. There is some underlying distribution that the learner doesn't know, and now it samples some points. And the goal might be well, you can't really identify the threshold exactly because you can't be guaranteed because everything is just random. But you could try to be fairly certain that you get close to it, okay? So then that depends, of course, on the underlying distribution, but we can somehow argue that something like 1 over epsilon, many examples will be needed to roughly with error epsilon identify that, threshold. But what will be looking at is a simplified, idealized world when we want to identify things exactly, not just close by. Well, then we can't have randomly chosen examples. One thing that you could do is look at active learning. You all have heard about active learning. There is a learning algorithm that selects a data point and says, well, tell me whether or not it belongs. Okay, so in that case, here with those grid points and grid points, you could even learn exactly with an active learner. What would you have to do? Well, you would basically do binary search, right? You would pick a point somewhere in the middle, and then say that point that I labeled 1 there, you would pick first, and then depending on, because it'll have a label 0, then you know the true threshold is to the right of this point, and you keep halving the space. So with log n many examples that you draw as an active learner, you will have identified the target exactly, okay? Now, what I am interested in is a model where there isn't an active learner, but there is a benevolent teacher. This teacher says, well, don't bother, I will give you examples. In this particular case, that teacher can make your life very easy. It can pick 2 examples, one just before the threshold and one right spot on, and then you will know, right? Because everything is black and white and true here, no noise, nothing, right? You will know exactly this is where the threshold is. So interestingly, in the active learning model, the number of grid points matter, but in the random model and in this teaching model, the number of grid points don't actually matter, right? How large a number n is doesn't really play a role. So here, if you're consistent, you will be able, as a learner, if you're consistent, meaning you guess a concept that agrees with the labels that you've seen, then you know after those 3 examples exactly what to do. So in this talk, I'm focusing on one question, like in this example, where the active learner really, the complexity depends on that number n. For the random and the teacher setting, maybe it doesn't. So one thing we wonder about is that what makes a concept class difficult or easy to learn in the random model is the same thing, possibly the cause of what makes it difficult or easy to teach in this exact model. So those are 2 completely different models, but somehow perhaps the combinatorics, the structure of the concept class, what makes learning hard or easy can be determined by the same thing. So towards that, I will first tell you something about a parameter in the random model that is known to characterize how difficult or easy something is to learn. That's called the VC dimension. Many of you will know it. And then I will introduce classical parameters from the teaching side. It's the so-called teaching dimension notion. And in this context, we also have to talk about what does collusion mean and how do we avoid it. There are lots of variations on this classical teaching model. I will introduce a couple of them. But then when we try to relate the complexity of these models to the VC dimension, which is the complexity that we study in the random model, then we will run into some trouble trying to get around that collusion-freeness. And what this talk is about is how much do I have to challenge the notion of collusion-freeness? Do I have to soften it up to get to relate the complexity of teaching to the VC dimension? And then I will show you a new teaching complexity parameter that we introduced in this NeurIPS paper That's the first and so far only known teaching parameter that is a complexity below VC dimension. But we had to somehow play around with the collusion-freeness to get that.
Can I ask you a quick question? Is this generalizable when you have more than just one concept? So if you have many concepts, like a multi-class kind of case, and for each class, you don't have just one threshold, you all have the two sides. So is this idea also generalizable in that context?
Oh, yes, yes, yes. So this particular example of a threshold function was just an example. The concept class can be any set of many, many, many concepts, okay? So here, for example, I'm going to introduce VC dimension. This is a parameter that can be applied, or evaluated for any kind of concept class. So we assume now we have any concept class, any set, any number, could be infinitely many concepts, and they're of any sort of shape. They don't have to be geometric shapes, could be anything. And now the VC dimension is defined to be the size of the largest subset of the underlying domain X, such that all the possible bit patterns for that subset X are realized by the concept class. What does that mean? I'm going to show with an example. So now assume we have the class of all axis-aligned rectangles in R2, like in the beginning. I'm claiming this dimension here is 4. What does it mean? It means there is a subset of 4 points of the R2, such that whatever 0, 1 pattern I assign to those 4 points, there will be an axis-aligned rectangle that is consistent with that 0, 1 pattern. But the same cannot be done with 5 points, okay? So 4 is really the largest subset. Okay, I've picked my 4 points here. That's where they are. I'm claiming all the 0, 1 patterns can be realized with axis-aligned rectangles. Why is that so? Well, this one realizes the all zeros pattern. It contains none of the points, right? This one has a pattern where one of the points is 1, and so on. Here's 2 of the points are 1. These 2 points are 1, whichever 2 I choose, I can find a rectangle. For whichever 3 I choose, I can find a rectangle. And of course, I can also do all 4. So all the bit patterns I can realize, but I cannot do the same thing with 5 points, because you can argue no matter how you choose 5 points in the plane, there will be one of them that is contained in the axis of the smallest axis-aligned rectangle containing the other 4. Like here, that center point, and then you go and find a rectangle that realizes this bit pattern. You won't, right? It doesn't exist. All right, that's why the VC dimension is 4. And it's all nice classical theory that shows that this VC dimension parameter characterizes how difficult it is to learn from randomly chosen examples, in the sense that you get upper and lower matching. They've been found to match a few years ago, sample bounds that are linear in this VC dimension parameter. Okay, so it tells you something about how difficult it is to learn the class. Just that one parameter, which is, a nice, purely combinatorial parameter, nice insight into something that, might not look only solely combinatorial only at the onset. So teaching dimension is quite a different parameter. Teaching a concept now means providing a set. So if I have a concept C, I want to provide a set T that depends on C, and that's labeled examples in it. And all these labeled examples have to be labeled accordingly to C, so they agree with the concept. But this teaching set T of C has to disagree with all of the other concepts in the class, in the underlying concept class. So if I pick a different concept from C out of that class, it has to have some inconsistency with that teaching set, okay? So then the teaching dimension parameter for the concept C itself, with respect to that bigger class of concepts, is simply the size of the smallest teaching set for that concept. This could be infinite in some settings, but let's for now not worry about that. The teaching dimension of the concept class now is say, okay, the concept class has lots of concepts in it. We look at the worst case. So what is the hardest to teach concept? Well, what is its teaching dimension? So we take the supremum over all of the teaching dimensions of the individual concept. So this is all old stuff down in the 90s, but still the basis of many of the things done today. Here's a very simple example. Look at the top table first, please. Here we have each column representing an element of that instance space X, and each row is a concept. And one entry now means, for example, C1 contains X1, but none of the others. C2 contains only X2, and so on. So here we have all the singleton sets. Now, if I want to teach, say, C2, how would I do that? Well, I'm going to tell you the concept you have to learn has a label 1 for X2. Well, there is only one concept in this world, and this concept class that fulfills this, so you know immediately. So the teaching dimension for each single concept is C, is single concept C is 1. So the supremum over a lot of ones is still 1. Therefore, this concept class has teaching dimension 1. That's like the simplest thing you could think of. But that simplest thing you could think of, well, everything goes downhill if you add just a single concept to it, namely the empty concept. So the only way these two tables differ is the last row has been added. Now, still, all the singletons have a teaching set of size 1. Still, this is the only thing in this column here with the 1, so nothing changes here. But if I want to teach this empty concept, even if I give you n-1 examples, you still don't know for sure it's the empty concept, because say if I take the first n-1, well, this one is going to look the same on the first n-1 columns. So this last buddy here has a teaching dimension of n, and so the worst case is now n. Okay, so just adding a single concept to the class can turn the world around with this parameter. Here's another example how easily things can change. If we look at circles in the R2 with positive radius, they have a teaching dimension of 3, because if I take 3 points on the circle, then there is really only one circle that contains those 3 points, right? 2 or fewer points don't do it. We don't have to go through that argument. That's not so hard to see. So the teaching dimension here is 3, okay? But now I'm going to say, oh, but I now care about filled circles. So I care about balls where the interior is part of the concept. Mm-hmm. Now I'm claiming the teaching dimension is infinity, because here, well, the 3 positive points obviously don't do it, because all larger circles will also be consistent with that. So I need to add negative points, right? So I'm going to add a bunch of negative points somewhere around the circle. But then, of course, if I want to learn exactly, just because of density of R2, I can always squeeze a dashed circle in there. That's going to be consistent. And so I could learn approximately, but I can't learn exactly, right? So therefore, I get this infinity. Now, I told you in the beginning, I'm looking for connections between the BC dimension and these teaching parameters. But unfortunately, teaching dimension, BC dimension are completely unrelated. They've got nothing to do with each other. The one of them can be 1 and the other are as large as you want. You can construct anything. So maybe though, this model of teaching also doesn't cast teaching in a very useful way, right? So perhaps we should think about teaching differently. So the idea that we've been going after for a number of years was the teacher selects helpful examples, and the learner should use the knowledge of the selection process, because here the learner is only just consistent. It doesn't know anything about how the teacher chose those examples. It doesn't matter, right? So, and this, also aligns with some work on human learning psychology. So humans do actually, they are sensitive to how the observations that they make have been chosen. So we have been looking for a while, and not just me and my group, but also others, at different smarter teaching learning protocols. And you know, for me, this work really started here, by the way, when I was a postdoc. So that's why you see Rob's name in some of my publications here. This is work that we did together here. And Marty Zinkovich was a postdoc here at the time. He got me onto the topic in the first place. So I haven't seen or heard from him in a long time, but I'm still happy that he started this. Anyway, so now you might say, okay, let's think of something a little bit more sophisticated, allow the learner to somehow react to how the teacher chooses examples. Why wouldn't you teach the balls this way? Pick the center point and the North Pole, right? That uniquely describes the ball. And if I, as the learner, know you choose the examples that way, you give me those two positive examples, and I say, I know what you're talking about, right? The reason my community would not like that is because they would say, okay, now look at these three positive examples. Okay, so the first two, I would say it's the orange ball, but now I'm not giving you two examples, but three, these three. Well, now I don't know, well, is it the orange ball? Or is the middle ball just one, middle point just one that was tossed in, and you're actually talking about this ball, right? So how would you know? And why don't we like that? Well, that comes from a classical definition of collusion-freeness. So let's look at what a teacher and a learner actually are. A teacher, we can think of as just a mapping. As input, it takes a concept and it maps to a set of labeled examples, right? It's like a compression. And the learner eats that set, C of C, and spits out a concept. And they're successful, they're matching if, of course, it spits out C when it has read the teaching set for C. So, but what we also want is for them to be collusion-free. And the classical definition by Goldman and Matthias says, okay, it has to be the case that if I give you a teaching set for C, and then I add examples to it, and those examples, that set T prime, are still consistent with C, that shouldn't throw you off. You shouldn't then suddenly say, oh no, I no longer think it's C, right? Just because you get more information. Okay, and this is what happened with these three examples in the ball. So that would be collusion if we did it this way. So here, if you add that third point, then you do not know anymore. So we did some research into this and tried to characterize what's the best possible teacher that doesn't have collusion. And that is a teacher that is what we call non-clashing. It doesn't have clash. So this is actually not hard to prove formally, but here's the definition of what it means to be non-clashing. So if you have two different concepts in the class, then it is okay if one of the concepts, say C1, is consistent with the teaching set for C2, but only if then C2 is inconsistent with the teaching set for C1. So they cannot both at the same time be consistent with one another's teaching sets. And that's all that you have to guarantee. So either C1 has to be inconsistent with the teaching set for C2, or vice versa, or both. But as long as you have that, then you won't have collusion, okay? We call that non-clashing just because of a similar notion studied in sample compression. So now the no-clash teaching dimension is what is provably the best teaching you can get without collusion. So a non-clashing teacher is one with this property that I just introduced. We say the order of a teacher is just the worst case teaching set size that it ever produces. Every teacher is a mapping, eats a concept, spits out a teaching set. These teaching sets of various sizes. The largest it ever spits out, that's its order, okay? So the NCTD, the no-clash teaching dimension, is now the best possible order that any of those non-clashing teachers could have. You know, there could be 10 non-clashing teachers. One of them has the the best worst case behavior, that one is the one who sets the bar, okay? Now, by the way, for those filled balls, no matter what dimension, you do have an on-class teaching dimension of 2, because how you get around this collusion is just throw away those center points and instead put the South Pole. So we have the North Pole and the South Pole, or actually any 2 diametrically opposed points, right? It cannot happen. So the red ball is consistent with the teaching set for the orange ball, but not vice versa. So always one of them will disagree with the set for the other. So just fixing it up this way, you get a non-clashing teacher, and that's the whole idea. So now, from now onwards, I will look at only the finite world. So X is finite, all the concept classes are finite. That eases some things, but a lot of what I say will also work the other way. So we know the NCTD is the best possible worst case complexity you can have for collusion-free teaching. We can, there's this model RTD, that was the one invented by Marty a long time ago. It is a very well-studied model of teaching. It satisfies an even stronger notion of collusion-freeness. There is a paper in which we characterize that. I won't go into the details. So it's, you could say, well, that Goldman-Mathias collusion-freeness isn't enough for me. I'm imposing more constraints. Then you get exactly Marty's model. And people have been trying to relate the complexities of these teaching models to VC dimension. All of the work here is that none of that was done by me or my team, but it's all published in either Nurex or Cold. So there are some people who really care about this stuff, and it's interesting stuff. So there was a group of people who showed that Marty's parameter, RTD, is upper bounded by a function quadratic in the VC dimension. We also know that it is not upper bounded by the VC dimension itself, because it can be exceeded by a factor of 4 or 5 over 3. But we don't know, is it upper bounded by a function linear in the VC dimension? We have no idea, no clue. For the NCTD, we don't know if it's upper bounded by a function linear in the VC dimension or even by the VC dimension itself, okay? The only model that we knew where there was an upper bound in terms of VC dimension was a model of sequential teaching, where you don't get a set like a batch, but you get elements in sequence, and then you can encode a lot in that sequence. So we, of course, somehow then all jumped on the NCTD, because that is the best known collusion-free notion, and we know it is definitely less than or equal to the RTD, and therefore it also has to be upper bounded by that function quadratic in the VC dimension. It inherits that upper bound of the RTD, right? But we have not yet to date found any concept class where even NCTD would be larger than VCD. So it's still a contender out there for being upper bounded by VCD, or at the very least a function linear in the VCD, but we don't know how to prove it. We just don't know. So this being our only hope to that date, we said, okay, maybe we have to look at things differently. Maybe we shouldn't be married to that notion of collusion-freeness. Okay, so you may have been in this situation. Your professor gives you a math assignment saying, prove statement S under the premises A, B, and C. You go ahead and you prove statement S using premises A and B, but you don't use C. Well, if you're a very self-confident student, you say, well, the teacher made a mistake. If you're like me, you would have said, oh my goodness, I must have done something wrong. Why do you think that? Because you believe the teacher gives you only information that's important, okay? So why shouldn't we think about incorporating such ideas, at least to some extent, in machine learning, where data is chosen in a benevolent way? So what if the learner assumes the examples chosen are important? Okay. Obviously, actually, that old collusion-freeness is immediately out the window. Why? Because it says if you add more consistent examples, it won't throw you off. Well, if I assume everything you tell me is important, it will sure throw me off, right? So, but what we did was go back to the old literature and said, was there ever any model where we didn't have that collusion-freeness? And that was also in the work I did with Robin Marley and Stefan Lange. That was a model called subset teaching dimensions, which has sort of been forgotten because it wasn't collusion-free, okay? So here, the assumption is the teacher and learner both know all of the minimal teaching sets, all of the best possible classical teaching sets for a concept. Now, then you would actually have two reasons to exclude a concept C prime when you see a set of examples. One reason, of course, the old one is, well, C prime is not consistent with the examples you've shown me. A different reason could be, well, you know, all the examples you show me are correct for C prime, but if you're a benevolent teacher and no minimal teaching set for C prime contains those examples that you've shown me, why would you select them in the first place, right? So you can't be talking about C prime, you just can't be. And that's why you exclude C prime from your candidate list. That was the original idea of that subset teaching dimension, STD. So here, this is the classical TD, teaching dimension setting. The teacher gives, say, 5 examples to the learner. The learner says, okay, that's, C is actually the only concept consistent with these 5 examples. So then that's a classical teaching set. Now, the teaching dimension would be 5 for this concept. But in the STD setting, maybe the learner says, well, if I just look at the first 3 examples, well, all the other concepts are either inconsistent with it or don't contain those 3 in their teaching set. So they wouldn't be good or important examples for this concept. You wouldn't use them, so you can't be talking about C prime. And now I've, in essence, reduced that teaching dimension to a subset teaching dimension of 3, okay? That's basically the idea behind it. So, and you can then argue this process will always terminate, then you iterate it, you keep doing that. You look at the sets of size 3, and then again, do they have subsets that are not subsets of other sets of, you know, and you keep, this is like something that you can iterate. And then you create that way the subset teaching dimension parameter. Really nice. I still to this day like this idea. Here is our old friend, those singletons with the empty set. So now assume you see a single negative example, xi is 0. Well, there are actually n concepts in that table that agree with this example. So there's only one that you can exclude based on consistency, but for those other singletons that agree with it, no minimal teaching set for those concepts would ever be using a negative example. A negative example is not important for those concepts. A good teacher would give you a positive example, right? So you know you can't be talking about any of the singletons. You must be talking about the empty concept. All right. So you have taken down that teaching dimension from n to 1. Okay. But as I said before, you don't get that notion of collusion-freeness. So then we said, okay, what if the teacher, what the learner now assumes the examples are chosen in it somehow as important examples, and then I must soften up that collusion-freeness idea. So now I'm assuming I have any kind of teaching model X with a parameter XTD. Okay, what would I want it to satisfy? Maybe I don't want it to satisfy that old, or don't need it to satisfy that collusion-freeness. And what you want it to satisfy could really depend to a large extent on your application setting, right? With your concrete situation. Some properties of these, maybe I listed 3 here, maybe you want 2 of them and not the 3rd one, maybe you want them all 3. So one could be what we call class monotonicity. It's quite intuitive. If you increase your concept class, so you throw concepts in, then that can only increase the teaching dimension in terms of worst case. You know, you're not suddenly making it easier. Another one could be, now suppose you're projecting your concept class onto a subset of the columns, right? So a subdomain. And let's assume this projection keeps the number of concepts intact. So no 2 concepts collapse through this projection. then I'm thinking teaching becomes more difficult because I may have thrown out the examples that are really helpful for teaching through that projection. I may have thrown them away and I may be left. And now I said, in essence, have fewer choices left what to teach with, right? But I have the same number of concepts left. So that can only make it harder. That's what we call domain monotonicity. Or sometimes we find it useful if at least we have some anti-chain properties saying, if I have two concepts, at least the teaching set for one of them should not be a subset of the teaching set for the other. Okay, those are just 3 properties that we thought could be natural. So does that make STD any more useful for our purposes? Unfortunately not, because it is not class monotonic. It also is not domain monotonic. It happens to have the anti-chain property just by design, but most importantly, it's also not upper bounded by any function linear in the VC dimension. So why all this pain? Yeah, because actually you just have to wiggle that definition of the STD a teeny tiny tad. So this is then what we came up with. How can we make it fit? So the STD, it looks at all the minimum teaching sets for a concept, right? All teaching sets, all the minimal ones, minimum, smallest size ones. Instead, how about we look at only one teaching set and maybe not even necessarily a minimum one, and start off with that and iterate the same definition of subset teaching, starting there, okay? So this is a little bit technical now. I'll just show you the technical definition. And basically, you start saying, well, first of all, I'm trying to teach concept C with all of its examples. So this is the set of all labeled examples, full information. Of course, that's way too many. Now I'm iterating. So this is the iteration 0 and iteration k plus 1. Always what I will do is I will take a subset of what I had previously while just ensuring that I don't create a subset of a teaching set of somebody else. Okay, here's my concept C. Here's my current teaching set for it. I find it too big. I want to make it smaller. All I have to make sure is I take a subset of this, but this subset is not contained in some other concepts teaching set. That's all. You iterate this, and here's the reason why I said we look at finite concepts and everything. Because everything is finite, that iteration just has to converge at some point. We can't make them any smaller anymore at some point. And then the order of the teacher that we then resolve. Yeah, Mike?
Is it unique though? Because couldn't it be multiple choices you could make about how to create the subsets?
Exactly. There are multiple choices. Okay. So it's not clear what you may end up with many different teachers. Okay. You look at only the ones that have the best order. Again, like in the no clash model, there are also actually many different teachers. And that's another property we looked at. So I love this question. It's because we also looked at, can we get teaching where the teacher that you create is sort of unique? You can't here. So, but we take any of the ones that has the best possible order you end up with.
But how smaller? When you take a subset, how small are you?
Whichever way you like. So I'm not saying that this is efficient to compute, right? But I'm saying there is a unique number that characterizes the smallest you could ever end up with, okay? And that number, that's the STD min, okay? And for lack of a better name, we just had to call it something like STD. And here's the results. Okay, so basically we had the TD and RTD and NCDD models before that are all really well behaved, the collusion-free, class monotonic, domain monotonic, anti-chain, everything, but unfortunately, either not upper bounded by VC dimension, or we just don't know, right? So then we dug out the old STD, but unfortunately it's you draw like a complete blank pretty much on everything that you want to have, but you just modify it a little bit and you get this. You get a model that is no longer collusion-free in the old sense, but it satisfies all those through 3 postulates. It's provably upper bounded by RTD and by VCD, not just a function polynomial or linear in VCD, by strictly VCD. And that is the core proof in this paper. That's that all goes to Farnam. He gets full credit for that. He came up with that proof, and it uses really nice structural properties of concept classes. So that was a really nice contribution of his. And yeah, so that's what we ended up with. And we found the first batch teaching notion that had a complexity upper bounded by VCD by softening up that collusion-freeness constraint. I want to mention this one because all of these properties that we list, like the anti-chain property, you might ask, well, how constraining is that? And how, or how liberating if you had only this, right? So we wanted to know if we had the anti-chain property alone, we quickly noticed you can teach, so if you have you have all bit patterns on n elements as your concepts, right? So the full power set. Assume you have the full power set of you have 2 to the n concepts over a set of n elements. You intuitively think, well, you need to show all n elements to teach. How would you distinguish, right? So if you have only the anti-chain property, you quickly see that you can do with much less. And we were worried, does it allow us to do with less, at least sublinear, right? Really strictly sublinear. That would have been a bit of a pain because anyway. So we actually figured out it's not sublinear, and we could nail it between 0.22 and 0.23 times n for all but finitely many n, which was a really interesting proof. And if the theorists like Mohammed and Zach were here, they might appreciate this. And it's a purely graph theoretic proof that actually got us this result. It uses the theory of bipartite matching, which, it's not completely obvious. But yeah, so that was a really nice side result we got from this, just to mention for those who have a theory heart like me. So to wrap up, we defined the STD-min notion, the first notion that concerns batch teaching has a sample complexity at most VC dimension, or even the first one known with linear in VC dimension as an upper bound. That meant we had to soften up collusion-freeness constraints. We instead then proposed some new postulates for collusion-freeness that could be useful in guiding the design of teaching models, hopefully. And STD-min satisfies them all. And the proof techniques, by the way, that we use, or that Farnam used to get this result, they're actually techniques that are also used in the context of a really important open conjecture in learning theory. The sample compression conjecture has been open for decades. And so really with this paper, we have new hope that we may have a new angle working on that conjecture too. We had an interesting observation on anti-chain teachers, but we also have some open stuff. For example, what's the relationship between NCTV and VCE? So the classical collusion-free teaching, can it be done with VC to mention any examples? Or also what natural postulates can you fulfill or can you not fulfill if you want to have a teaching notion upper bounded by VC dimension? So does that somehow constrain what you can say about teacher and learner, how they can communicate? So I hope that you will have some questions, but not just about this. I also would like you to know that I'm open to questions about all sorts of stuff. These are just projects that are currently open and not even all of them. Those are things I'm working on that I selected might interest some people here. I don't know how I came up with RL. It's something that some people might find interesting. So I'm working on something with RL agents that learn from each other's mistakes in a cooperative game setting. I thought maybe somebody would want to help me wrap this project up. I'm working on learning when to forget in self-directed online classification. So a setting where the learner picks a pool point and says, I want to classify that one next, and then gets the correct feedback, but then has to choose whether to update its memory, whether to retrain its model or whether to just forget the point. When should you do an expensive update and when should you just ignore? I'm working on classification based on diverse clusterings. That's something that I'm working on with NIDI. I picked up one of her papers and we've had a couple meetings and we're working on that. I'm working with Levi and we have a new student, Amir Hussein, here. He's over there. Hi, Amir Hussein, welcome to Alberta. So we're working on program synthesis type stuff. I'm working on, I think some of you will love this, learning from contrastive examples, like counterfactuals in teaching. Okay, I'm not looking specifically in any direction. I'm working on notions of stability in machine teaching. How can we make, machine teaching more robust so that because we can go out of that exact world into a more, approximate world, but then we need robustness. There's also a lot of theory stuff. I'm doing program synthesis with noise, where we learn SFA, symbolic finite automata, approximately. With Rob, I'm still working on learning from strings that have certain relations on their substrings. I'm working on approximation algorithms, if somebody's interested, for near optimal aggregation of user preferences. So we have preference models of users. We want to say, oh, we've got 100 users. They're all pretty similar. I want to represent them with a single preference model instead of 100 different ones. Connections between machine teaching and bipartite matching. So I can now get sucked into graph theory, and I also looking at learning graphs, learning hypergraphs, learning discrete dynamical systems. So lots of interesting stuff, and I hope you have lots of questions for me. Thank you so much for enduring all of this just for a couple slices of pizza. I'm really glad you took the time. Thank you. Randy.
I have, I think, 3 questions, but they're all related. And they're related to the learning programming language fragments that I'm talking to you about. Okay. Also to stability. So here's the intuition I get from the properties of the stream or batch of teaching examples. Is that the teacher can be a good teacher in which there's no collusion, what you call collusion, but the teacher can be a less than optimal teacher. And so there can be at least 2 kinds of collusion, accidental and intentional. Both of those will lead to attenuation and finding the program that is the characterization of the concept. Now, the same thing is true in inductive logic programming, where you're looking for characterizing the minimal models that cover the examples. So my question is, in that search, if you could define a metric in that search, like you started with C++ program, can you do a bounded, hopefully not exponential test to say whether a fixed data set is going to be misleading or not and guide that search? Because that's essentially what you're doing this smaller finite case, right?
Yeah, so, I just had a meeting with Levi yesterday. We had talked about related things and we're really just starting. I really don't know, but this is kind of the hope. So I want to, so we talked about, okay, I have a search space. It may be way too large. Can I make certain assumptions in advance that make it manageable? What assumptions do I have to and can I make on the original positive data that I see? We're also thinking about taking example programs that we have, and then you can modify them a little bit. This is like augmenting your data set. You change the program a little bit and just run it through a compiler, so at least you will see is it still correct, rather than making really expensive tests on their value. Right?
In the case of the stability, one of the ways I think about stability is that the ordering of labeled examples can matter and can give rise to non-monotonicity in the, the unrobustness or not. That's important in the inductive logic programming world, because if you can identify those streams and reorder appropriately in detecting this kind of collusion, then you can reduce the search space. Even when it's infinite, you can still make informed steps to this program covering examples versus this one.
Yeah,
that's another way to think about it.
Yeah, and that's really relates to the notion of importance. Once you commit to saying, okay, the teacher is going to give me important examples, then you might as well think, well, the examples the teacher gives me first are the most important, right? So that then brings the whole sequence thing into play.
Now we have a theory of bad teaching that we could use on our teaching evaluations. Other questions?
Mike.
You know, when I think about the collusion-free property, I try to think about what we're trying to rule out. Right?
Yeah.
It feels like, you know, you probably think of the theory terms and I think of the example terms. So I'm going to go with examples. You know, I could just use a space of X. Like, it doesn't even matter what label I give to it. Just the fact that I pick this point might identify the class, right? If you give me a continuous space, then I can in fact identify any finite subset of concepts in one.
Yes.
So you've lost collusion-free, and then maybe you try to recover it by adding these three other postulates to try to say, well, we didn't throw everything away.
Yeah.
I guess I didn't understand those three postulates, and maybe you can help me understand how we were still ruled out.
Yeah.
Where I could just use my X to identify my class.
Yeah, so if you use your X, like you use X number 17 to identify concept number 17.
Yeah.
Now, if I do a projection and throw out number 17 and I no longer have it available to teach, then you know, I can't do that anymore. So this kind of teaching.
Second property, I thought the domain one just said it's the property is that if I throw stuff out, it gets harder, which indeed this gets harder.
Yeah, right, but your notion of teaching doesn't work anymore. It breaks down, right? You don't. So I see where the confusion is coming from. But then you can no longer say the teaching dimension is one, right?
Right. So I thought that property was just saying the teaching dimension has to go up when that happens, which indeed it will.
Yeah, it's more complex.
Yeah. So yes, I see what you're saying. Okay, so
So then I'm wondering if it's the anti-chain one, because that one I didn't understand.
No, this one has totally the anti-chain property because you don't have any teaching set containing anything else. The problem is, of course, with that kind of this kind of type that you described, it works very well if you have exactly as many points in your space as you have concepts, right? Else you already can do it. So if you're in a finite world, it won't work because if you say you've got countably infinitely many, then you could use that kind of scheme, right? But you cannot do it, say, if you've got a finite concept class, because in general, you'll have way more concepts than you have instances. Because else you have something, if you fall back, you have as many concepts as you have instances, you actually essentially fall back to just a different way of encoding the singletons. And those should be doable with one.
So you're essentially not ruling that possibility.
So
you're ruling it out in the sense that, well, then it will not give you, if you have as many instances as you have concepts, you're willing to accept that that has a teaching direction.
Yes, if you have a finite space and you have exactly as many instances as you have concepts, then I would say, okay, why not? Right? I mean, not that you would say, I particularly love this.
It feels funny to me because in a sense,
yes,
for this to work, for me to teach a student this way, I first have to explain to the student my encoding.
Yes.
And then I can teach them in one go.
Right.
But to teach them my encoding, I basically taught them.
Right.
The concept as well.
Yeah. Yeah. No, and then maybe you want to say, well, in this particular setting, I don't think if I have as many concepts as I have instances, I don't think those three postulates are enough for me. I want something else. Right? You could say that too. Right. So this is the tricky thing with the collusion-freeness, that it really comes down to what's your world, right? What makes sense, how to define collusion-freeness. Intuitively, when you speak about the notion of importance might already mean you're colluding, encoding too much, but you can think of setting some. So what we tried to get a connection with at the time we studied the subset teaching dimension, the notion of importance, we had some vague connections to things like nearest neighbors. So the examples that you use to distinguish a concept from its nearest neighbors in the class, they're somehow more important than others, right? So but yeah, you're right. I mean, in a setting where I have 10 concepts, 10 instances, that goes to put. That's correct.
Yeah. This question helped me phrase my last question, I guess. And it's I'm not sure I understand anti-chaining either, but it seems to me that if you can prove a bound on a teaching set that's anti-chainable, that's anti-chaining, that you improve stability, because anti-chaining to me is sort of directly related to the flip-flops of non-monotonicity, and it gets reduced if you can prove anti-chaining. Is that right?
I'm not sure I understand your question. So let me just tell you
about whether the calculation of anti-chaining improves stability, and does it improve stability because in your search for the correct covering of the teaching concepts, stability comes when you don't go back forwards and backwards, right?
Okay.
And so that's what I think of anti-chaining is saying. There's stability in that chain so that there's less flip-flopping.
So stability can mean, of course, a whole whack of different things.
Yeah.
So the anti-chain property really just means if I'm teaching this concept with this teaching set and that concept with that teaching set, one teaching set is not contained, it's not a subset of the other.
Oh, I see.
Right? That's all so that you that an anti-chain, a set of sets is an anti-chain, if no set is the subset of another. So that's all there is to it. I don't think it specifically relates to stability. Rob?
Yeah, I guess we hit 1 p.m. and so people should, feel free to leave or anything like that. But I did actually have a question, and it relates to my own question. And that is, so when I first saw the definition of collusion-free, I couldn't understand intuitively how it had anything to do with my intuitive understanding of what collusion-free was. So after all these years, I've actually figured out, why it actually means collusion-free that day, or is the reason formally capturing it. So now we have your 3 properties, and I'm back to kind of square one, because I don't really see how they have anything to do with my intuitive concept of collusion-free. Okay, so and obviously there's a gap, and that's the other part of my question, or maybe it's the only important part of the question is I assume the collusion-free has those properties.
Yes.
And then, so then what other properties does it have that aren't in that list of 3? Like, I don't know if you've ever sat and written them down or anything like that. But
yeah, it's not that we have one single thing that fills that gap. I mean, we then say if you have those 4 properties, then together, or I mean, if you have 10, then you and a whole bunch of them and make that the 4th one. It doesn't really matter. So we don't have a correct characterization of what exactly that gap is as a nice, beautiful property. But yeah, so I understand that intuition is kind of hard to grasp and is for us too. But things like when we talked about subset teaching, I mentioned way back when, because there is such a clear process of how to define it. And it also makes sense to use just those minimum teaching sets. And there didn't seem to be intuitively any collusion in it. And with it, for example, you can also not do what Mike said for the 10 concepts, 10 instances, won't end up happening there either for, say, specifically subset teaching dimension. And yet it does not satisfy the collusion-freeness notion. Well, mind you, it doesn't satisfy the other 3 either. So it does it, well, just one of them. It's an anti-chain. That's all there is. If it satisfies none of these properties, then still it seems like, I'm sure you remember the definition fairly well. And at the time we did that research, we really felt like this is intuitively, in some sense, collusion-free. And it doesn't even satisfy it.
Right. So used to call collusion-free, used to call them coding tricks.
Yeah.
Phraseology has disappeared, but that's why Mike's example is really a coding trick. You are encoding the name of the concept.
And you can apply. You can if theory is so neat because as soon as you have the axiom of choice, you can encode all sorts of stuff. And then sometimes I run into this problem. How do I get around the axiom of choice? Because it allows me to do all sorts of wacko things in coding that that I shouldn't think should be possible. But yeah, so yeah, then you can get into really awful stuff there. No, this is not resolved. So these are really important questions because we cannot really nail down how to exactly define collusion-freeness without getting into areas that we didn't ever want to get into. Yeah.